Hello, my name is Joshua Hammond, and in this activity of process dynamics control, we're going to model an HIV infection using coupled differential equations. The HIV infection, which spreads to AIDS, is a human immunodeficiency virus that spreads by attacking the body's white blood cells. Recent advances in medicine have allowed us to treat this virus, and thus it's a very interesting case to study. We'll be modeling the count of infected cells, healthy cells, and count of virus within a human body using differential equations for each and looking at how these interact with one another. Let's now discuss how we'll model the HIV virus's progression within the body using MATLAB and our differential equations. Here we'll want to make a plot as a finished product that will look something like this, with 3 lines that model the healthy, infected, and virus cells within the body. So if we come down in this assignment, we'll create a semi-log Y plot, and we'll discuss these 2 bullet points here. We'll discuss what terms we would adjust to match the HIV lab data that measures the patient and the virus in a patient, and then we'll discuss what the effect of a new antiretroviral drug would be on our differential equations. So let's go ahead and take a look at our conditions and our differential equations. We have first our initial conditions right here. We have 1 million healthy cells, 0 infected cells, and 100 virus particles within our body. Now let's look at the parameters and especially how those parameters relate to our equations. So we have 6 parameters in this model. We have the new healthy cells rate per year, the death rate of healthy cells converting to infected cells, death rate of infected cells, death rate of the virus, and production of the virus by infected cells. So let's look at those in context. We have our DH/dt, so the change in healthy cells per time. In this case, that's per year. So we have Kr run 1, so we have 100,000 new healthy cells per year, minus Kr2, so death rate of healthy cells times healthy cells. So 1 in every 10 healthy cells will die every year, and that's just a fact. It has no dependence on the virus. Then we have Kr3 times H times V. So Kr3 is healthy cells converting to infected cells, and that's proportional both to healthy cells and the count of virus as well. And we'll see this term, this Kr3 times H times V, in the other 2 terms as well, or in the other 2 equations as well. We'll have the change in infected cells per time is exactly the opposite of that. So it's how many cells are converting to infected cells. So it's Kr3 times H times V. And then we have minus Kr for I. Kr4 is the death rate of infected cells. So 1 in every 2 infected cells is going to die. And that's where we have that coming in. Finally, we have the change in virus count per time, so per year. So the virus is going to go down the number of infected cells, the Kr3 times H times V term. And that's going to happen because when a virus enters a cell, it's going to enter that cell and it's going to expend itself within that cell in order to make the cell make new viruses. So whenever we have an infected cell, it's because 1 less virus exists. It expended itself making that infected cell. We're going to have the virus count times 5 is going to be how many viruses die per year. That's because the virus death rate, the lifespan of a virus is less than a year. So we're going to use that to approximate the total number of viruses that would die in a given year. And then plus Kr6. This is where the viruses are coming from, besides that initial amount. So Kr6 is the production of virus by infected cells. So for every infected cell, when that affected cell dies, what happens is that virus comes in, it programs that cell to make the proteins for a new virus, and that cell eventually bursts, and all the new viruses come out. So we're going to say that that will produce 100 new viruses per infected cell. So we can kind of look at how these equations are interrelated. That the healthy cells come down dependent on the virus count comes down dependent on how much the virus dies already, but it comes up with proportion to the infected cells, and the infected cells come from infecting healthy cells. So these are 3 interrelated systems of equations. Let's briefly discuss how the function works. So we have the function named simulate infection, which takes the argument t and z. Z will be an array where we store H, I, and V in a column vector. And so we'll extract each of those values at any given moment using indexing. Next we have the parameters, which remain constant throughout this. And we have our equations, our differential equations for healthy cells, infected cells, and virus cells, as we discussed before. Finally, we'll return these three in a change of Z array, which has dH dt, di dt, and dv dt in a column array. So we'll go ahead now and we'll run this first portion that initializes our constants and our initial values. We see those just on the right to make sure that they're output. Next we're going to go ahead and we're going to initialize our times array and our initial conditions, that Z0 array. Next we're going to go ahead and we're going to simulate our differential equations from time 0 through all the times points, so from year 0 to year 15. And finally we're going to plot that. To do a semi-log y plot, we're going to first index H, I, and V with the first column, second column, and third column for healthy, infected, and virus cells. And we're going to use the semi-log y term to make a semi-log y plot. So we'll go ahead and we'll plot that. It'll take a second and we'll just observe this right here. Now let's discuss the final questions. First, what we would do to match our data to virus count within a patient. Since we have an actual data for V or virus count, we would adjust the parameters within V as well as the dependent equations, so the K1 through K6, to be able to fit this data more clearly. We'd be able to use some sort of fit like a least squares fit that would be able to adjust these parameters until we have minimum error from our experimental data. To model an antiretroviral drug, we first need to understand what that drug is doing. That's the first step of all modeling. Here, infected cells are inhibited from producing new virus cells. We could model this either with a new term in our differential equation or by lowering the amount of virus that is produced by each infected cell.